Hello students, welcome back. We just completed sections 1 and 2, and let's go to section 3, the matrix exponential. Now, I believe there are many students who just breeze through sections 1 and 2 because they just went through linear algebra or they already know a lot about matrices already from pre-calculus. It's okay, but this one must be new, so pay attention. Here is a definition of the matrix exponential, and this is a kind of quantity that we are looking for. And by the way, this is the very same expression as the definition of the real exponential function. We define it like this. Instead of I, we have 1, and instead of a, that's going to be x. And this is the definition of the real exponential function. It's based upon the Taylor-Maclaurin series expansion. And then replace x by z, then this is complex exponential. We didn't do any kind of graphs or any limit theorem or anything. This is nothing more than just repeated addition and multiplication. Same here, so well defined. Potential problem may be the convergence, but then again, the denominators are growing so quickly that it's okay. The interval of convergence is negative infinity to infinity here. The radius of convergence is infinity there, no problem there. The same thing goes for matrices. We're talking about square matrices here, n by n matrices, so all the additions and multiplication are well defined, and we have only a to the whatever power and I, so they're all commutative. Everything works out fine, just like real number arithmetic and complex numbers arithmetic, as long as you don't divide by anything, and here there's no division, so everything makes sense. That's a matrix exponential. Now, how useful is this? This is going to be a little bit more useful version. As a matter of fact, this can be a little bit confusing because I'm using same character A, but matrix A here and matrix A there are not related, to tell the truth. Maybe it's better this way. Replace this A by another matrix B, because that's the definition. It works for all those square matrices, and of course B is another square matrix, then this one makes perfect sense. After defining like this, yes, you can do that. And then I'm going to define B as A times T, where T is a scalar, so this is scalar multiplication. And then if you plug in this AT in place of all the B's there, here, there, first power, and then the second power, third power, fourth power, and so on, then of course you're going to get this expression there. So this one down here is actually a special case of this one, to tell the truth. But it's written in a little bit confusing fashion because you may get an illusion that this A and that A may be related, but they're not related. Now, how useful is this one? It turns out that it is possible to write down the system of first order linear differential equations. We started like this, using all those derivatives intertwined like this into a matrix form like this, B part here, C part there, and then a bit of a manipulation later. Let's keep it open. Starting from here and then like this, and name this one as A and that one as F, then you get this standard form which corresponds to this. And please note that this one is heck of a lot simpler than this one. in a sense that we have only one derivative for each line. And then this kind of conversion allows us to study the standard form here. And the standard form here can be solved through, let's see, the typical thing, solution for homogeneous system plus a particular solution. And the general solution for the homogeneous system, it follows this expression. Y is e to the at times y star, and there's a direct parallel with one-dimensional case. If this had been the differential equation, is e to the at power times something, and that something happens to be the initial condition. And previously we went through the separation of variables and so on, all those things to deduce those. Compare this with that. Exactly the same, but this one is for real numbers and this one is for matrices. So if we establish matrix exponential, then the solution of this homogeneous first-order linear systems with constant coefficient is pretty much done. And then of course we may have to consider these particular solutions as well for non-homogeneous systems, but that's for another day. So, ready for matrix exponential? Okay, let's assume everybody's ready and let's go. Here's the definition and then the very easiest case. The easiest case is for diagonal matrices. In that case, the computation is really easy. Turns out, all we need is the exponential of the diagonal entries, which we call eigenvalues. The parallel for this is that, replacing a by at. Likewise, if you replace d by dt, then you're going to get this exponential, which is pretty simple as well. Just multiply by t. It's a scalar multiplication, so multiply t to each diagonal entry. And exponential of diagonal matrix is just exponential of those diagonal entries only, so we have e to the lambda t power. So this one down here is parallel to this version compared with this goes for that. Now, how do you prove these, by the way? Just do some brute force computation. Let's see. Yeah, we have to do this kind of computation. No. In general case, we have to do this kind of computation where in place of A we have D. So identity matrix, great. Original matrix D, great. And then D squared, D cubed, D to the fourth power, we need those kind of things, and here are those computation. D squared, this is D times D, and if you do your computation, you're going to get all those lambda squared. And then this is D squared, and then times D, that's going to be D to the third power, and your computation will give you lambda to the third power in the diagonal. And then if you repeat it to the fourth power, fifth power, and so on, and this is arbitrary kth power, again, you're going to get k power in the diagonal. So, if you put everything into this Taylor series expansion, so d to the k power is just these, where k power appears only for diagonal entry, and everything else is just 0. And then we have 1 over k factorial. Okay, divide each by k factorial. and then add them all up. Then you're going to get the power series, the Taylor series expansion for each diagonal entry, which will give you exponential of the diagonal entry at each place. So there goes the proof, and even if you did not follow the proof, it's going to be still okay mostly. You can use this formula here. E to the diagonal is exponential of those eigenvalues. Special case, when d is equal to 0 matrix, in that case, diagonal entry is all 0, so we have e to the 0 power all the way, and they're all 1s. Conclusion, e to the 0 power is equal to 1, or in the matrix version, e to the 0 matrix is equal to 1 matrix, the identity matrix. Okay, we just went through the very simplest case, the diagonal case. And then let's do a little bit general case. Oh, here's a repetition. E to the 0 power is equal to 1, or e to the 0 matrix is equal to the identity matrix. Now, next rule. One of those exponent rules which require the commutativity, which is not always true. For in general, this may not work. But for this, when we have two matrices, A and B, which commute, then we have the exponent rule. The proof, by the way, is exactly the same as the proof of the exponent rules for real number arithmetic, which we discussed in lesson 1A. Here, all I did was copy and paste the very same proof, and then change x to A and y to B, uppercase. Why can I do this? Because we have exactly the same arithmetic rules, addition, multiplication, and all those properties, associativity, distributivity, but most importantly, commutativity. Yes, now we do. And follow all those, and we can prove that e to the a power times e to the b power is equal to e to the a plus b power. It's really tedious, elementary but tedious. We'll say we are done with those, and we're going to use it. Now, a special case. When b is equal to negative a, in that case, negative a and a, of course, commute. This is equal to a times negative a, because what is negative a? Simply multiply scalar multiplication, negative 1, and then I can multiply scalar to the next matrix. So no problem there, they commute. So I can apply the exponent rule. And here we go, e to the a power times e to the negative a power. We got e to the 0 power, so that's I. Conclusion, e to the negative a, this is the inverse matrix of e to the a power. Here's another interesting result, therefore. The original matrix A is just a square matrix. It may not be invertible, but e to the a power is always invertible. And the inverse is e to the negative a power. So a doesn't have to be invertible. E to the a power is always invertible. Interesting. Alright, so much for all those exponent rules and all those algebraic rules. Let's do some actual computation, and looks like we'll have enough time for only one problem here. And let's do that. Let's consider this problem. A is given like that, and then let's calculate e to the at power. Basically, I want this computation where t is a scalar. So how do you do that? Well, this identity matrix, a times t, okay, multiply by t, so 0, nothing there, 1 times t, negative t, 0, like that. And then a squared times t squared, a cubed times t cubed. We need these kind of things, especially all those powers. And then, of course, we have to consider all those factorials as well later on. But the important part is a to the k power. Let's do those computation. 0 power is just I, no problem there. 1 power is just a, and then multiply by t, we get this matrix. No problem there, that's simple. Now, a squared. Here's a squared computation, a times a. So first row times first column, 0 times 0 is 1. 0 times 0 plus 1 times negative 1 is negative 1. That's what I meant to say. Sorry about that. First row, second column. 0 times 1 plus 1 times 0, that's 0. And so on. Assuming you do all those matrix multiplication and you get a squared like this and multiply a squared times t squared. Voila, we have this intermediate result. By the way, this is where we are headed. So we are up to here. Next, a cubed. All right. This is a squared times a, and do the computation. Again, the matrix multiplication. First row times first column, first row times second column, second row times first column, second row times second column. I'll assume everybody can do it now. And then in the end, we get this after multiplying t cubed. Another matrix multiplication, t cubed times a, so we have a to the fourth power. A to the third power times a. Turns out that's identity matrix. And then a to the fifth power. Identity times a, so it's original a again. And the pattern repeats. We are back to I, and then a squared, and a cubed, and so on. Pattern repeats like this. So add them all, and you're gonna get this. Let's see. How about this 1, 1, and 3? So 1, and then 0, and negative t squared, 0, positive t to the fourth power, 0, and negative t to the sixth power, 0, positive t to the eighth power, and so on and so forth. So what do you get? And then denominators are all those factorials to begin with. They're all factorials. We get alternating sign, plus minus, plus minus, plus minus, for even powers only, and that's going to be cosine. What if you look at the 1, 2, and 3 here? And I claim that is sine. How does it work? Well, that's 0, and then 1 times t, and then 0 minus t cubed, 0, positive t to the fifth power, 0, negative t to the seventh power, 0, and positive t to the ninth power, and so on and so forth. What do we have? We have all the odd powers with alternating signs with sine function. And we can determine the other entries as well similarly. Conclusion, e to the at power is this matrix. So, we wanted to find out the matrix exponential, especially e to the at power, and we found at least one method. Multiply all those powers with a to the k power times t, and then put all those in and try to find out the pattern. Is there any clever way? Well, there are some, and we're going to discuss those in next module.